Using the definition of the derivative, which is f prime of x equals limit, and we'll just use this one as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Using this every single time will get tedious, and we're going to find in section 3.2 that we can use some generalizations. We can find some rules that work for everything, such as if, let's say, that our f of x was some constant. So f of x is some constant, and I want to know the derivative of a function if it happens to be a constant. So let's look at how that might play out if I were to just do it for any value of c. So f prime of this c is the limit as delta x goes to 0 of, now f of x plus delta x, so let's just say our delta x right here is x plus delta x right here. So what would that function value be there? That function value is c minus, and what is the f of x value at x? That would also be c all over delta x. This yields the limit as delta x goes to 0 of 0 over delta x. This reduces even further to the limit as delta x goes to 0 of 0. And I know what the limit of a constant is because we looked at that in the previous chapter. This equals 0. Oh my goodness. So derivative is slope. What's the slope of this line? Well, it's 0. So if I have f of x equal to 5, that means f prime of x, f prime of x equals 0. If I have g of x, let's say, equals 72, g prime of x equals 0. I now have a generalization for a function that's a constant. I know that the slope is 0. We're going to go and find some more rules. So let's come up with a rule for something raised to a power, and we'll end up calling it the power rule. So for this one, let's say that my f of x is just some x to the n, and then, as you know, I can then, for polynomials, I could just extend it using my sums, my sum laws for limits, which is what ends up happening. So I'd like to know what f prime of x is for anything of this form. I'm going to use this definition of the derivative. It'll make it pretty simple, at least I hope anyway. And x minus a. Okay, now I'm going to replace. So I have the limit as x goes to a of just plain old f of x, so that would be x to the n, minus, replace my x with an a, that would be a to the n, and then this would be my x minus a. Ooh, that's pretty close. If I factor this thing, now I don't know how many terms there are because n can be anything, but I have some factoring rules, and I know that it would end up looking something like an x minus a, and then this next one would be the x would be reduced by a power, and then whenever they were FOILed out or multiplied out, I would end up having an a times that x to the n minus 2, because he would reduce by a power, and then the next one would be like a squared x to the n minus 3 plus, there'll be who knows how many terms in the middle, and then plus, if I were to work them all out, this would be an x squared a to the n minus 3 plus x a to the n minus 2 plus a to the n minus 1. if I factored out an x minus a. And of course I still have this on the bottom. That dealio would cancel. Now I don't have any reason why I can't just do plain substitution for this limit. So I'll get a to the n minus 1 plus a times a to the n minus 2 plus a squared a to the n minus 3 plus who knows how many terms in the middle plus, let's see, oh, x squared, so that would be a squared a to the n minus 3 plus substituting a times a to the n minus 2 plus a to the n minus 1. Nice. Combining like terms, a to the n minus 1 plus that would be a to the n minus 1 plus that would be, oh, that's because I'm adding exponents here because I'm multiplying, that's a to the n minus 1. Isn't that cool? And whatever I did in the middle there, they would all be a to the n minus 1s as well, because this is going to be a to the n minus 1, this is going to be a to the n minus 1, and this is, of course, a to the n minus 1. So I could say that there were going to be n of these terms, n terms here. Because if I were to count how many of them there would be n of them. So I could just say, well, if that's just the definition of multiplication, really, so that's just n times, because it's however many a to the n minus 1 times however many terms there are. Oh, f prime of x, if I have something of that form, I can just do this from here on out and I don't have to use that limit definition. So let's see, if I have f of x equals x squared, that means f prime of x is, just take that power, and we call it a power drop because really this power drops down, that's a 2, and then my x is to the, just subtract 1 off your exponent to the first, or just plain 2x. Let's play another one. Let's say g of x equals x to the 5th. That would mean g prime of x equals 5x to the 4th. And I can use this rule for all of my powers from here on out. So they want us to find the derivative of a few of these. This is one way to write the derivative. Just says take the derivative of your function with respect to x. This dx on the bottom means with respect to x. I'm going to use the power drop here. 9, bring it down, subtract 1 off your exponent, bam, don't even have to use the limit definition. The derivative of just a plain old x, well, he's an x to the first power if I'll remember, and that would mean drop down my 1, so that's a 1 times x to the 0, and if x is to the 0 power, that is just a 1. And what that means is, if I were to look at this, the graph of x looks like this, somewhat, and his slope is 1, and the derivative is nothing more than the slope, so I'm good with that. This is 2 to the 8th, and 2 to the 8th has a value, let's see, what 2 to the 5th is 32, 2 to the 6th would then be 64, 128, 256 I think. Whatever it is, doesn't really matter to me, it's a constant, so the answer there is 0. Okay, I don't just always have constant functions or something to a power. Sometimes I have something that might look like, let's just say I had a g of x that was 3x to the 4th, and I wanted to know what that derivative is. So I've got to figure out what to do with this multiple here and see how it works. So let's use, we're going to say my f of x happens to be Alright, so let's say I want to know what the derivative of c times some f of x is. So we are going to, so I want to know what the derivative of that with respect to x is. I'm going to use the limit definition. I'll say the limit is delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So let's see if I can come up with a generalization for this. Limit is delta x goes to 0 of this would be c times f of x plus delta x minus c times that f of x all over that delta x. Okay. I can pull that c out of both. Alright. Then I can use my limit laws and say I have a constant times my function, and that means I can just pull the constant out front because it's going to be the same as that constant times that limit. And I now have, which still looks pretty messy, but what I have is this equals the constant times your derivative, because this chunk ola here is the definition of the derivative. So if I have a constant times my function, I can just say that it is the constant times that function. So here, if I want g prime of x, I would take the 4, using the power rule, bring it down front, multiply it by that 3, and I get 12 x to the, and he drops a power third, and there would be the derivative there. We've got a couple here. This is kind of like looking at negative 7/8 is your constant. So I'm going to say negative 7/8 times the 11 drops down, and then x to the, and he drops a power. So this would be negative 77 over 8 x to the 10. This is the same as writing derivative with respect to t. I'm going to write 3/8 t to the 1/2 power. Here's my constant right there. I'm going to power drop, multiply it by that. So I'll have 3/8 times 1/2, and then I'll get t to the, and it's going to be 1/2 minus 1. So 1/2 minus 1 is a negative 1/2. This one's kind of messy. 3 over 16, and then that would be t to the 1/2, negative 1/2 power. That would best be written as 3 over 16 square root of t. If you're given something in terms of a radical, you need to leave your answer in terms of a radical. If they give it to you in terms of a fractional exponent, you can leave it there. It's okay to go back and forth, but you want to leave your answer as the problem was presented. Now, the beauty of working through all these proofs is that once you do, then you can use these theorems throughout the rest of the course because they've already been proven. So let's prove this sum rule. H of x, I'm just going to say, is this f of x plus g of x. And I would like to know what h prime of x is. I'm going to use the limit definition. Limit as delta x goes to 0 of h of x plus delta x minus h of x all over delta x. So this is going to be the limit as delta x goes to 0 of, and h of x happens to be f of x plus g of x, and I can then replace, because this is just the sum of two functions, so I'll write f of x plus delta x, and then plus g of x plus delta x. And what I just wrote down right there was replacing this right here is this stuff right here. I just replaced the x plus delta x with that, replace x with x plus delta x, sorry. I'm trying to do too many things at once here. Minus, and then I'm just going to minus off that function, and the function is, so here's h of x there, so f of x plus g of x all over delta x. Alright, I'm going to regroup a little bit. Equals limit as delta x goes to 0 of, I want the f's collected and the g's collected. F of x plus delta x minus f of x, and then plus g of x plus delta x minus g of x when I distributed that minus sign, all over delta x. I'm going to do something here that I call bust a fraction. So it's the limit as delta x goes to 0. I'm going to bust this into two separate pieces, and I can know that using my limit laws I can do that. Minus f of x all over delta x plus the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. And if you'll notice, each of these chunks is just f prime of x plus g prime of x. This proof can then be extended to a subtraction. You'll just change the sign right here to a subtraction, and you would get the same exact result. You would get the f prime of x minus g prime of x. This is a very powerful theorem, and it allows me to do all kinds of polynomials. So here I've got, you'll notice I'm using the power drop rule, I'm going to use the constant rule, and I'm going to use this sum formula that I just came up with, and this derivative will be the 3 drops down multiplies by the 2, that's a 6w to the second because he drops a power, plus 9 times 2 because that power drops, that's 18w to the first, minus, this is just, since this is w to the first, his power drops, is minus 6 times 1, the w then goes to the 0 power, which is then a 1, and then the 4, because he's a constant, just drops out of there. And there's your derivative. We're now going to look at the derivative of e to the x. First off, they go ahead and define how the number e is actually given. The number e, and this is a definition, so it's nothing to prove, we are just stating this fact right off the bat. The number e itself satisfies this condition. So with that, we're going to use this theorem, we're going to use that definition to prove this theorem. So if I look at f of x equal to, let's say, e of x, and I want to find f prime of x, I want to find the derivative of e to the x, I'm going to use this definition as h goes to 0 of f of x plus h minus f of x all over h, and I'm going to do my substitution. This would be the limit as h goes to 0 of e to the x plus h minus e to the x all over h. And then with that, I see that I have an e to the x in both of those, so I'll factor that out. The limit is h goes to 0 of e to the x, and then what do I have left? I'll have an e to the h here, minus I'll have a 1 there, and I'll have an h here. I'm going to use my limit rules for multiplication and say times the limit as h goes to 0 of this e to the h minus 1 over h. Next, what I'll do is use the fact that this is the definition of e, so this whole chunk right here goes to 1. Then I've got that this equals, the limit is h goes to 0, so I'll do direct substitution. The derivative of e to the x is e to the x. Isn't that cool? So let's do one. Let's do f prime of x here, given this particular function. So I've got a constant times my e to the x, so the constant is just 4 times whatever that derivative is. The derivative of e to the x is e to the x, minus power drop rule, 2 times the 3 is a 6, x drops a power, and there's this function's derivative, which means it's the slope. Alright, so let's do some of these problems. Okay, write an equation of the line tangent to the graph. So of course they asked me something about a graph, so I go ahead and draw it on there for you. I did. I'm going to need, if I want an equation of that tangent line, I'm going to need the slope. That means I need to find the derivative. I'm going to take the derivative of this function here, derivative of 2x. I'm going to use the power drop rule, bring down the 1, that's just going to be a plain 2. X to the 0, of course, is 1. Minus, this is like negative 1/2 times e to the x. So if I have a constant, that's negative 1/2 times whatever the derivative of e to the x is, and that's just e to the x. Okay, so there is my derivative, which is the slope of any of these tangent lines along this curve. So there it is. So if I want the slope, I'll just plug into this formula. And it appears to me that f prime, the slope, is dependent only on x, so that's the only thing I'll have to plug in. 2 minus 1/2 e to the 0. This would be 2 minus a half, which would be 3/2. So there's the slope at that point. So at this point right here, right there, the slope right there of the tangent line, and if I were to try to draw that tangent line, it would look like this. I want the equation of that line that's tangent to that point. The slope there is 3/2. So I know the slope, and I have a point. So I'm going to use what I call the point slope formula, which is y minus y1 equals m times x minus x1. You use that a bit in chapter 1. Now you're going to have to recall it. Plugging in, because I have a point and I have a slope, y minus y1 is negative 1/2, so that's plus 1/2, equals m, that's 3/2, x minus 0. Cranking that around a little bit, I get y equals 3/2 x minus a half. There's the equation of my tangent line. So this right here is the equation of that blue line right there. Alright, now what do they want next? Find the point on the graph of f where the horizontal or tangent line's horizontal. So they just want to know where the slope is 0. We'll do that in a different color, purple. So they want to know right there. Where is that? So it's going to be right there at the top. But they want to know where it's horizontal. So they want to know where the slope is 0. Well, if here is the, let's see, here's the equation for slope. Where is he? There he is. There's the equation for slope. So where is that sucker? There's the equation for slope. So I want to know where the slope is 0. So that's really what they're asking you. Where is slope 0? So I'll just say 0 equals 2 minus 1/2 e to the x. Just finagling this around a little bit. 2 equals negative 1, oops, negative 2 goes negative 1/2 e to the x. Multiplying, that would be 4 equals e to the x. And if I want the exact answer for this, I'm going to take the natural log of both sides, and I will get x equals natural log of 4. And that is the place. Oh, they want the point, so there's the x value, so I actually have to give you the y value as well. So this is going to be the y value of the original function, because that's what I'm looking for. So y in this case is 2 times x minus e to the x over 2. So the y would be equal to 2 times the natural log of 4 minus e to the natural log of 4 over 2. Y equals 2 natural log of 4 minus, that would end up being a 4 over a 2, which is just a 2. And then that's my y value, so the point would look like natural log of 4, 2 natural log of 4 minus 2. There's the point. And I could crunch those numbers and get an approximate decimal value. Just wanted to show you their graph because they actually did that. Here's our answer here, and they actually crunch the numbers, and if you do the natural log of 4 you'll get 1.39, and the y value at 2 times natural log of 4 minus 2 would be the 0.77. In this next problem, they're wanting me to find where the slope, let's see, does a tangent line have a slope of 6? So I want to know where the slope is 6. Well, derivative is slope, so I need to find the derivative first off. F prime of x, oh, it's writing weird again, hold on. Alright, so I need to find the derivative of that function. So I would get power drop rule 6x squared minus power drop, that would be a 30x plus 24 using power drop rule again. I need to know where this slope equals 6. I'll say 6 equals 6x squared minus 30x plus 24. Solving this, 6x squared minus 30. Pad's not working real good right now. Subtract 6 from both sides. That'd be plus 18. I'm going to factor. X squared minus 5x plus 3. And that's going to be quite messy. So messy, in fact, that it's going to require the quadratic formula. So minus b, that'd be a 5 plus or minus square root of b squared. Negative 5 times negative 5 is 25. 4 times a times c, that would be a 12. It's ugly 12. All over 2 times a, that would just be a 2. So this would be 5 plus or minus square root 13 all over 2. Crunching those numbers, if you want to, you'll get something like 0.697 for the minus one, and for the plus one you get 4.303. So here are the exact values of where you will have a slope of 6, and here are the two x values that are approximate values. So x equals either one of these, well, this probably should do a little wavy guy bracket to say it almost, and x is identically equal to those things with the square root in it. This one wants me to find the derivative, or find the point at which it has a horizontal tangent line. That means the slope there is equal to 0. So I need to find the derivative. F prime of x equals 3x squared minus 12. Set that derivative equal to 0. And then solve for x. 3x squared equals 12. X squared equals 4. And then x equals plus or minus 2. Now they didn't just ask me for the x values here, they wanted the y value, the entire point, so I need both the x and the y values. So for x equal positive 2 and x equal negative 2, I need to get those y values. So I go back to my original function so I can get those y values. Y would be 2 cubed minus 12 times 2 here. Y equals 8 minus 24. I believe that's negative 16. Therefore, this point is 2, 16. The other one, by equals negative 2 quantity cubed minus 12 times negative 2. Y would be equal to negative 8 plus 24. And y is, in this case, a positive 16. Alright, makes sense that it's symmetric. Negative 2, 16 would be your point for this one. Alright. This next definition tells me what a higher order derivative means. And a higher order derivative means what we've been doing is called the first derivative. If you want the second derivative, you take the derivative again. If you want the third derivative, you take the derivative 3 times. That's what it means to say that I'm finding a higher order derivative. Let's play with example 6. If I want the third derivative, f prime, so this is the first derivative, is, using my power drop rule, 3 times 3 is 9, x squared minus 5, the constant term drops. F double prime, or the second derivative, is take the derivative again, power drop rule, that would be 18x, and the constant drops. The third derivative is 18. There's the answer to the A part. The next wants me to find the third derivative again, y prime. I'm taking this with respect to t, obviously. So that would be 3 plus 2, because that's my constant, is e to the t. The derivative of e to the x, or e to the t, is just e to the t. That's a constant. There's my second derivative and my third derivative, and all the rest of the derivatives would look just like that too, wouldn't they? Alright, and if you have any problems with this, I hope to see you at the Collaborator, or hopefully you're emailing me letting me know. And you've been through the proofs of these, and you can now use any of these rules.